Alright, so now we're going to focus on the concept of differentiability, which is the ability to differentiate. Okay, well that's great. But the ability to take the derivative. So when can we or can we not take the derivative, which again, rate of change of the curve, slope of a tangent line, slope at an instant, all of those things are kind of interchangeable at this point. Alright, so try to apply the limit definition of a derivative to find f prime if f of x, we can just kind of pitch that right there, is equal to the absolute value of x. Well, let's think for a second about our graph of the absolute value of x. Looks like this. Alright, so if we think in terms of drawing in those tangent lines, we should be able to take the derivative everywhere, except maybe at 0 we might have a little bit of an issue, which we talked about in preview week, because of local linearity or lack thereof. But let's do some math and actually justify our work. Imagine that. So if we want to find f prime of x, we know that that's equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Well, our function is the absolute value of x, so that means our derivative is going to be the limit as h goes to 0, the absolute value of x plus h minus the absolute value of x all over h. Alright, well if you plug in 0, you get 0 over 0, which means you need to keep going. Well, to keep going with algebra is a little bit tricky with those absolute values. I'm going to suggest here that because we have subtraction in the numerator, let's try multiplying by a conjugate. Well, I know if I multiply by the conjugate in the numerator, I have to multiply by that same conjugate in the denominator. Okay, so doing some foiling, this is where I want you guys to use a little bit of your math brain. I know it's in there somewhere. If you take the absolute value of x plus h, we know that that is going to turn into a positive quantity because absolute value represents distance, and distance is measured positively. So if we take the absolute value of x plus h, which we know is a positive value, times the absolute value of x plus h, which is again the same positive value, then it should stand to reason we get x plus h squared. It's going to be positive, and a positive times a positive yields another positive. So even if x plus h itself had been negative, if I square it, it's going to turn positive, and that's really what we're worried about here. Well then, same thing can be true about absolute value of x and absolute value of x. If I multiply them together, it should stand to reason that my outcome should be the same as squaring x. You're taking a number times itself and then making it positive, so to speak. As we've learned from previous examples, in the bottom, we are not going to want to distribute that, because ideally something is going to cancel out that will help us. Remember to keep that limit, otherwise it's no longer a tangent line. Alright, so keeping going with our algebra, we're going to have x squared plus 2xh plus h squared minus x squared over this lovely denominator. Alright, so things that are going to cancel. X squared and x squared. H is going to cancel with that h and one of those. So I'm at the limit as h goes to 0 of 2x plus h all over absolute value of x plus h plus absolute value of x. Well now, as h goes to 0, this h is going to drop. This h is going to go to 0. So we're going to actually be left with 2x over the absolute value of x plus the absolute value of x, which is 2 absolute value of x. 2's can drop out, and we are left with f prime of x being equal to x over the absolute value of x. So if we think about this function representing the derivative, there is a value on this function where our derivative then would not be defined. Hopefully you're telling yourself that at x equals 0, f prime of x is undefined. Because if you plug in 0, right, we're going to divide by 0. This is not a limit thing, this is a problem, right? If we think about it from the graph perspective, this graph right here is going to be one of these. It's actually the same graph as if you had the absolute value on top and the x in the denominator. So our derivative function is undefined at 0, which means our derivative, or the slope of our tangent line here, is undefined at 0. And if you remember from preview week, the problem with that is it's a sharp corner. It doesn't matter how close you zoom in, you don't know where your tangent line is supposed to be because it's just kind of floating and wavering on that sharp corner. We don't know where to draw that tangent line, and therefore our derivative is undefined at 0. So a sharp corner is going to be 1. Thinking then about the graph x to the 1/3, if you need to graph it on your calculator, you may. Otherwise, I'm going to give you this picture right here. Okay, this is what x to the 1/3 looks like. And if we start to draw in these tangent lines along the curve, everything's all well and good. We've got things that are locally linear. If you zoom in, slope, 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 slope. And then we get to this this vertical tangent line. Before then, these kind of start to mellow themselves out a little bit. Well, this vertical tangent, this one in green, I'm actually going to make it yellow so it stands out a little bit more. If we're talking about the derivative being the slope of the tangent line, what is the slope of this yellow line? Hopefully you just told yourself the slope is undefined at a vertical tangent. Which means our derivative does not exist wherever that vertical tangent may be. At this case, it's at 0 because of this function, but this graph might have been shifted over like this, in which case that vertical tangent would have happened right there. And if we're looking for the slope of that yellow line, the slope is undefined, which means therefore the derivative is undefined. All right. And then also, if you think about it in terms of a discontinuity, we know that we have jumps and we have asymptotes and we have holes. We cannot have a derivative at that discontinuity because you can't draw a point that's tangent if there is no point there to draw it in. All right? So even if your function is smooth and differentiable, we're going to have problems where we have a corner, that was like the absolute value graph, a vertical tangent line, which is like this one, a discontinuity, and then there's also this thing called a cusp, and that's like the little bird graph. And that has similar reasoning as the corner, right? Where do these tangent lines get drawn in? Nobody really knows, right? It's not locally linear. So if something is locally linear, then it is differentiable, which means you can take the derivative in that neighborhood or near that value where it's locally linear. A graph like the absolute value, or like this cusp graph, x to the 2/3, you could take the derivative all along here, all along, all along, all along. It's just right here at that cusp where we have a problem. Likewise, a graph that's continuous everywhere except for maybe a hole, you could take the derivative everywhere except for at that discontinuity. So if something is differentiable, that means it is continuous. Because if you could take the derivative, that meant your function had to have been continuous. If your function is not continuous, then you can't take the derivative at that value. Okay? But what about if a function is continuous, but not differentiable? That's going to be at the cusp, corner, or vertical tangent. So derivatives do not exist at discontinuities. That might be a hole, so removable, or a jump, or an asymptote. Okay? Next place they fail to exist is if we have a vertical tangent. That was that yellow line. Because the slope of a vertical tangent is in itself undefined, which means the derivative is undefined. And then at a cusp or a sharp corner, because those things are not locally linear. And remember, we're talking about zooming in super close on that function until it looks like a line. Well, at a cusp or a sharp corner, you're never going to get there. It doesn't matter how far you zoom in. Alright, so the last thing then to talk about is an alternate form of the derivative. I know we're just getting used to the fact that f prime of x is equal to the limit as, oh my gosh, cannot write. The limit as h goes to 0 of f of x plus h minus f of x all over h. It's that difference quotient, right? Subtraction and division that we've been working with. Well, that's all well and good, but let's talk about what happens if I want to know my derivative at a specific point where x is equal to c. So instead of looking for the derivative of any point along the curve, I instead want to focus in on one specific value. Well, that's a pretty simple exchange then that needs to happen. Instead of x, I want to plug in c. So maybe I want the derivative at x equals 3. Well, that means anywhere I see in x, this is a problem when I get tired, I want to plug in a c. So that definition is the same. Okay, we're just talking about at a specific location. So now when you FOIL things out, like if this had been x plus h to the third, this might be 3 plus h to the third, and this would just be a numerical value because you would have already plugged in your 3, in this case, to the function. So another way to think about this, looking at a specific point, f prime of c, okay, if I decide that I want x to be equal to c plus h, well, that means I can take this limit definition of a derivative right here, and I could write that as f of x, because I just said x is the same thing as c plus h. Okay, so that's all I did there. Then, this is going to be minus f of c, no big deal, over, now I need a way to replace this h in my denominator. Well, using this relationship over here, if I get h by itself, h is equal to x minus c. So this h can be replaced with x minus c. And now, I don't want the limit as h goes to 0. I replace my h with x minus c. So I actually want x to get closer to c. Now, if we think about that in terms of a graph, if I ignore this part with the limit, and I just look at this right here, I'm talking about some function. Here's a point x, and here's a point c. And right now, I'm finding their secant line. Right? This is just regular slope, f of b minus f of a over b minus a. No big deal. But as soon as I put that limit in front, as x moves closer to c, okay, x is getting closer to c, that means that this point right here is moving closer to this one. And so our secant line is actually turning into a tangent line. So this is just one more way to write the definition of the derivative. Really, they're all very similar. You can use them all, okay? This first one finds it at any value of x. This will find it at a specific point c. This will also find the limit at a specific point c. So slope of the tangent line, derivative, all of that stuff. We will do a warm-up like this together in class, so don't stress too much about it. Make sure, though, that you have these 3 definitions. This is going to be the one that we use most often. Most often, most often, most often. But you do need to be aware of these other 2 for AP purposes.